So hello everyone, welcome back to Codeverse Coders. So today we'll be doing artificial intelligence and machine learning numerical lecture. In our earlier lecture, we have studied artificial intelligence basic concepts like BFS, DFS, UCS, A star algorithm, AO star algorithm, and much more. So today we'll be starting with the machine learning part. In machine learning part, we'll be doing different types of numericals based on models like KNN, logistic regression, support vector machine, and many other models. But it's really important to have a basic foundation of all these models before starting the numericals. So let's start. So this is a first question. The first question says that you are given a data and you're told that under certain physical constraints, the model must pass through your origin. Derive the estimator beta bar using SSE minimization and compute its value. Then you have to use it to calculate your beta naught and beta 1 and which model has lower SSE. So let's start. First, we can see that they are in the form of x comma y. I hope it will be visible now, x comma y. Now we can also say that the values of xi are ranging from 1, 2, 3. These are the only three values that are there in our x coordinates. Whereas if we see in our y coordinates, yi, we can see coordinates like 2, 2 and 4 only. See 1, 2, 3. There's 1, 2, 3. Then there's 2, 2, 4. Then 1, 2, 3, 2, 2, 4. You may be seeing the pattern. So that is what I am writing in the form of xi and yi. Then after this, we know the value of x bar. If we calculate the value of x bar, taking all of them, right now in xi and yi, I've only written the first three. You have to further write 1, 2, 3, then 1, 2, 3. Here also 2 to 4, 2 to 4. Then you calculate your mean of x, you'll get it as 2, and your mean of y as 8 by 3, that is 2.67. Now, the formula for SSE is equal to summation of n to I is equal to 1 to n yi minus beta xi whole square. Now here it is really difficult to calculate because we don't know the value of either beta. So we need something in terms of our x and y's. So we'll calculate the first derivative with respect to beta. So we'll write derivative of SSE with respect to beta is equal to minus 2 of summation xi yi minus beta xi is equal to 0. Then after that, when we solve this part, that is summation xi yi, I'll just erase it. It's not working. Summation xi yi minus beta xi whole square is equal to 0. Now we can see that the beta value of beta bar is summation xi yi upon summation xi square. Now, this can be computed because we know the values of x and y's. So now we'll calculate x summation xi yi and summation xi whole square. So your summation xi whole square will be equal to basically 3 into 1 square plus 2 square plus 3 square. You'll get it as 3 into 14, that is 42. Then summation xi yi will be 3 into 1 into 2 plus 2 into 2 plus 3 into 4. This will be repeating 3 times. So we'll on solving, you'll get it as 54. Therefore, beta bar comes out to be a summation xi yi upon summation xi square 54 upon 42. This comes out to be 1.28, or to be precise 1.286. Now this was the first part. Second part is calculate beta 1 bar and beta naught bar. So beta 1 bar is equal to summation of xi minus x bar yi minus y bar upon summation xi minus x bar whole square. Now this can be reduced and written as summation xi yi minus n x bar y bar upon summation xi square minus n summation x mean square. On solving, we'll put the value of summation x bar y bar 954 minus n comes out to be 9, then into 2 into 8 by 3 upon 42 minus 9 into 2 whole square. We have calculated these values here. Now on solving this, you'll get it as 1. Then you'll calculate your beta naught. You get it as y mean minus beta 1 x bar. Now y bar is 8 by 3. We got this as 1 into x1 bar, x bar, not x1 bar, x bar is 2. So 8 by 3 minus 2 is 0.667. Now, the unconstrained model, that is y is equal to 1x plus 0.67, will have a lower or equal SSE. Now, the constrained model is a specific case of a unconstrained optimization. That is, the only difference is the beta naught is equal to 0. That is, it is a best fit line. Now, any non-zero value of beta naught is guaranteed to reduce the SSE further. We'll write this down also. Any non-zero value of beta naught by LSM is guaranteed to reduce the SSE further. So this was our first question. I hope this part is clear. First, what we did was we calculated SSE. We then differentiated it to get an expression based on x and y. Then what we did is we calculated our beta 1 and beta naught values. There could be another way to solve it. The second part was about an unconstrained model, right? So in that, there's another formula, that is, when we write y is equal to beta naught plus beta 1x, we can also write beta 1 bar as sxy upon sxx. Now, what is this sxx and sxy? So Like when we calculate SXX, we calculate its difference with respect to the mean. Every value minus mean whole square. Second value minus mean whole square plus third value minus mean whole square. Similarly, when we calculate for SXY, 1 minus 2, and then second 2 minus y bar. 2 minus 2, 2 minus 8 by 3. Then next value will be 3 minus x bar, 4 minus y bar. So you'll get your SXY. On cancelling further, you'll get your beta 1 bar. Then for beta naught, you apply the same formula, y bar minus beta 1 x bar, and you get your beta naught. Now, in case of the first one that we calculated, we got y is equal to 1.286x, if you may remember. But through the second method, we got a different answer. We got it as y is equal to x plus 2 by 3 or 0.67. Now basically unconstrained model here has lower SSE. Why? Because forcing through origin can increase the error. Forcing through origin can increase error. Constraining the line to pass through 0, 0 reduces the flexibility and prevents the model from minimizing SSE freely. So we understood this with the help of two different methods. One is this method seems to be simpler but has more calculations associated. If you want to go with this, you can solve it by this method also, but I prefer the first one. So now let's move on to the next question. A bank uses the following model to predict load default. Load default, this is the equation that is given to you all. Now, if a customer has debt to income ratio of 0.4, what credit score would result in 50% probability of default? Now, first let's write the equation. Z1 is equal to minus 10. This would not be. Z is equal to minus 10 plus 0.05 of credit score plus twice of DTI, debt to income ratio. Now you are given in A part probability of 0.5. So what we'll do is we'll calculate the probability. This is given to us 1 upon 1 plus e to the power minus z. This is the formula associated. Now probability is given as 0.5. So therefore 0.5 into 1 plus e to the power minus z is equal to 1. Now when we take 0.5 to the other side, we get 0.5 e to the power minus z is equal to 0.5. E to the power minus z is equal to 1. Now in this case, minus z should be equal to 0 to get the answer. That means your z is equal to 0. Now you put it in the equation, you'll get 0 is equal to minus 10 plus 0.05 CS plus debt to income ratio is given in the question 0.4, 2 into 0.4. By this we'll get the credit score as 184. I hope this would be clear. Now B part. If a customer's credit score increases by 20 points, what happens to the odds by default? Now there's another formula that you all need to remember. Z is equal to log P upon 1 minus P. Now the new equation that we'll have after the increment will be, so we'll write this as Z1, Z2, This will be minus 10 plus here 0.05. Is it 0.05? Yes, 0.05 into x plus 20 plus 2i's into dti. Now, on solving it, minus 10 plus 0.05x plus this will become 1 plus 2 dti. Now, if we calculate z2 minus z1, it will come out to be 1, that is equal to your delta z. Therefore, log odds increased by 1. E to the power delta z is equal to e to the power 1 is equal to 2.718. So therefore, what happens to the odd by default? It increases by 1. And you also have to calculate the value of e to the power delta z, that comes out to be 2.718. C part. If a bank decides to be more conservative and sets the threshold P as zero point 0.7, what will happen to logit z at the boundary be positive or negative? So P is equal to 0.7. This is what? This is your threshold. We know the formula z is equal to log P upon 1 minus P. You are given P here, if you may notice. So your log of 0.7 upon 0.3. This will be approximately 2.33, and log of 2.33 comes out to be as 0.847. This is greater than 0, therefore positive. The boundary logit z is positive. So this is our answer to question number 2. Now let's move to the next question. So this is our next question. In this question, it says a researcher is testing a model P y is equal to 1 is equal to sigma of w into x on a small set of binary data 1, 1 and 2, 0. The researcher proposes two possible values of WA and one of WB. Now, write the likelihood function of these 2 points. So we'll solve partwise. So likelihood function. The formula is L of W is equal to pi IPI of yi 1 minus pi of 1 minus yi. Now here you are being given your P of I as sigma of wxi. This is given. So we'll calculate first the values. For point 1, 1, we'll get sigma of w into 1 is equal to 1 minus sigma of w into 1 to the power 0. Please have a look. W into 1, this is your P of I, right? And 1 minus P of I to the power of 1 minus 1 is 0. Now if you have 2, 0, so you'll have sigma of W, comma point 2. We are multiplying W and X. So W into 2 raised to the power of 0. And then 1 minus W into 2 to the power of 1 minus 0 is 1. Then we have the answer as 1 minus sigma of 2W. Here we get this, and here we got sigma of W as the answer. So therefore your final likelihood function will be, you take this as common, 1 minus sigma of This is your first part of your answer, and this is the second part. You multiply. This is your answer. So basically, you need to know the formula, and after knowing the formula, you have to apply the value of the P function to the points that you are given in the question. Next is log likelihood you will have to calculate for W and WB. So the formula is LW is equal to log of capital LW. For WA is equal to 0.5. You have, we all know the formula of sigma z, right? 1 upon 1 plus e to the power minus z. Now when we calculate sigma of 0.5, we get it as 1 plus 1 e raised to the minus 0.5. 1 upon 1.607, you get it as 0.622. After that, you'll calculate sigma of 1 upon 1 plus e to the power minus 1, 0.731. This is what you get. Now here we calculate sigma of 2w. This will be equal to 2 into 0.5. That is 1. To put these values into this, we need to know the values of one is sigma of w and 2w, that is 1. Now on calculating, you basically put the values first in your capital L. You get it as 0.622 into 1 minus 0.731. 0.167 is the answer for your likelihood function. Your log likelihood will be equal to the log of this function, that is 0.167. You'll get it as minus 1.79. Now this was for WA. For WB, now sigma minus 0.5, 1 plus 1 plus e to the power minus 0.5. This will become plus. You will get this as 0.378, and sigma of 2w is equal to sigma of minus 1, 1 upon 1 plus e, 0.269. Your likelihood function will be 0.378 into 1 minus 0.269. This will come out to be 0.276. Now, putting the value in your log likelihood, minus 0.5 is equal to log of 0.276. You'll get it as minus 1.2. Now, since your 0.276 is greater than 0.167, therefore the better parameter based on the likelihood function is w is equal to minus 0.5. Choose parameter is equal to higher likelihood. Very important. So this was our third question. Let's move to the fourth question. Now this is on your hard margin SVM. You are given points x1, y1, x2 and y2. Set up the primal optimization problem. So let's start. You are given R square as the small training set in R square. So your basically primal problem will be equal to minimum of half of W square, such that yi into w transpose xi plus p is always greater than equal to 1. First, for both the points, let's check if this condition is being fulfilled or not. First, x1 and y1 will put their values. So yi is 1. Your xi is basically 1, comma 1 plus b is greater than equal to 1. This comes out to be w1 comma w2 into 1 comma 1 is equal to, this comes out to be w1 plus w2 on solving the matrix. W transpose x1 is equal to w1 plus w2. So here the value of min. Now first, I know this would be confusing to understand, so I'll explain it in an easier way. Forget this as of now. You just understand on what I'm making you write. Leave this part. So now, like when you take your x1 and y1, just see what I'm putting. You put w1 into x1, 1, plus w2 into x2 plus b is greater than equal to 1. I hope this would be easy. So you get w1 plus w2 plus b is greater than equal to 1. Now when you put x2 and y2, you'll get it as minus 1 into w1 into minus 1 plus w2 into minus 1 plus b. w1 plus w2 plus, no, minus b will be greater than equal to 1. This will be a second one. This is confusing, so I'll erase it. Minus b is equal to 1. These are the two equations that we get. Now the final primal problem that you'll have will be the minimum of half of the sum of squares of both, such that the two equations are satisfying each other. This is all. You had to first fulfill these conditions based putting the values of x1 and y1, x2 and y2. Then use the primal problem formula, that is this formula with respect to these conditions. Second, construct a dual Lagrangian LD alpha and find the optimal multipliers alpha 1, alpha 2 using the constraint alpha yi is equal to 0. So basically your LD of alpha. Now here we have 2 points with us. So this LD of alpha will be equal to alpha 1 plus alpha 2 minus half of summation of alpha I, alpha j, yj, x transpose I, xj. This is basically a dot product part. Now for 2 points we'll have these 4 cases. That is x1 transpose x1, x1 transpose x2, x2 transpose x1, x2 transpose x2. On calculating them, we'll get 1 into 1 plus 1 into 1. This will be 2 minus 1 into 1 plus 1 into minus 1 minus 2. Then similarly, when you calculate it, you get here you will minus 1 to minus 1 into minus 1. You'll get it as plus 2. Now you'll start putting in the values. half of alpha 1 square. 1 into 1 into 2 plus alpha 2 square minus 1 into minus 1 into 2 plus 2 alpha 1 alpha 2 1 into minus 1 into minus 2. This will be equal to half of 2 alpha 1 square plus 2 alpha 2 square plus 4 alpha 1 alpha 2. Cancel it with 2, you'll get alpha 1 plus alpha 2 whole square. This part which we have done in this cloud, this is your summation part only. This part. So now when you substitute it to the main equation, I'll do it on the next page. So here LD of alpha 1 plus alpha 2 minus alpha 1 plus alpha 2 whole square. Now, if you read the question, you are given a constraint alpha I yi summation is equal to 0. So that is alpha 1 into 1 plus alpha 2 into minus 1 should be equal to 0. By this, we can say that alpha 1 is equal to alpha 2 is equal to alpha. Now you substitute this in LD alpha, you get 2 alpha minus 2 alpha whole square. On differentiating with respect to alpha, you get 2 minus 8 alpha equal to 0. Alpha is equal to 1 by 4. We get the values alpha 1 and alpha 2 as 1 by 4. How? As they are all equal. C part. Now there's a formula of W that is summation of alpha yi xi. Now we will start putting all the values. We get W is equal to 1 by 4, that is alpha 1, yi into xi plus 1 by 4, y2 into x2. On solving this, you'll get 1 by 2 and 1 by 2. Now, yi w transpose xi plus b is equal to 1 for b. Now, on putting the values for point 1 first. So, 1 into 1 by 2, 1 by 2 whole transpose, 1 by 1 plus b is equal to 1. Now that we have found the value of w, we'll put the values. On solving, you get 1 by 2 plus 1 by 2 plus b is equal to 1, which gives us b is equal to 1 minus 1 is 0. Talking about the hyperplane, w transpose x plus b is equal to 0. 1 by 2 x1 plus 1 by 2 x2 is equal to 0. You get x1 plus x2 is equal to 0. So this is basically your hyperplane. Now when we talk about geometric margin, the formula is 1 upon w. This is mod of w basically. So 1 upon under root of 1 by 2 square plus 1 by 2 whole square is equal to 1 upon 1 by root 2. You get it as root 2. This formula is also very important. Plus you get the value of geometric margin as point under root 2. This was the fourth question. Now let's move to the fifth question. Now you're given ya alpha a, yb alpha b and yc alpha c. Now here you have soft margin SVM. In case of soft margin SVM, the value of C is equal to 10. You're given your points A, YA is equal to 1. I don't have to write it because it's there. So now, here we are talking about based on the KKT complementary slackness conditions. So this is basically your KKT condition for soft margin. When it is between 0 to C, you calculate the value of Fi as Yi into W transpose Xi plus B is equal to, if it comes out to be 1, it is on the margin and it is also support vector. If alpha is equal to 0, that means this function value is always greater than equal to 1. That is outside your margin. If it is equal to C, less than equal to 1. So there could be three cases. Either it's on the margin, either it's inside, or either it's misclassified point. So this will be decided based on a slack variable. In our first part, we have alpha is equal to 5. Now on checking condition, we can see that it is between 0 and 10. That means in this case, your value of F is 1, exactly on margin. Thus, your A is a support vector. Now B part. Alpha B is equal to 10 is equal to your C. So now this is the last case. That means F of B is less than equal to 1. Now for such case, we have Yi into W transpose Xi plus B greater than equal to 1. Minus this. This is basically a extra variable, that is a slack variable that we talked about here. Now, if it is exactly on margin, its value is equal to 0. If it is inside, it is between 0 and 1. And if it's a misclassified point, we get it greater than equal to 1, not equal to greater than 1. Now, since it's equal to C, it will be either misclassified or inside the margin. It is not equal to 0. So that means, therefore, it will always be greater than or equal to 0. Now, C part is saying, is point C a support vector? Does it lie inside or outside? Now, alpha C is 1, comma, alpha C is basically 0. So this is the second case, that is FC is greater than equal to 1. This is outside margin. Therefore, not a support vector. This is the next question. This is question number 6, where you're given a classification decision tree for a binary target. At the root node, you have 100 samples, 60 for class 1 and 40 for class 0. The two splits are as follows. One is for child 1 and child 2. They are given for us the two types of splits basically. So calculate the Gini impurity for the of the root node. Calculate its ratio for both the splits. Which split is preferred? So let's start first. The formula For Gini impurity for your binary classification is G is equal to 1 minus summation of Pi whole square. For root node, we are given that N is equal to 100, class 1 60 and 40. So therefore, let's calculate P of 1. This will be 60 upon 100, 0.6. P of 0 will be 40 upon 100, 0.4. So therefore, the value of G comes out to be 1 minus 0.6 whole square plus 0.4 whole square. 1 minus 0.36 plus 0.16. This will be 0.48. This will be a G of root. Next part says do it for both the splits. For split A, child 1, it is in 30 plus and 10 minus. Yes. So for split A, G1 is equal to 1 minus 30 by 40 whole square plus 10 by 40 whole square. You will get it as 0.375. Then for child 2, 1 minus 30 by 60. Now this denominator is the total. 30 plus 30, 60 plus 30 by 60 whole square. So after solving, you'll get it as 0.5. Now this value of split, this will be compared after calculating for both child 1 and child 2. 40% of child 1, 0.375 plus 60. We are seeing the total upon the grand total. So 40 upon 100 into 0.375 into 0.5. This will come out to be 0.45. For split B, G1, child 1, 1 minus 50 by 70 whole square plus 20 by 70 whole square. This will come out to be 0.408. For your child 2, 1 minus 10 by 30 whole square plus 20 by 30 whole square. This will be your 0.44. Similarly, we'll calculate split as first total is 70 into 0.408 plus 30 upon 100 into 0.44. Your value will come out to be 0.419. This split will be preferred. Why? Lower Gini impurity. Split B. This was your second. Now for your third part. Now information gain is basically entropy of root minus weighted entropy of children. Now entropy formula you all may be knowing, minus summation pi log of base 2 pi. So first let's calculate for the root. So root entropy is equal to minus 0.6 log 0.6 plus 0.4 log 2.4. This comes out to be 0.971. Now for split A and B, similarly like we did earlier, we'll calculate first for split A and then for split B. C1 के लिए minus 0.75 log 2.75 log 2 of 0.25. You'll get it as 0.811. Then for child 2, similarly, apply the same formula. 0.5 plus 0.5 log 2 of 0.5. On solving, you'll get it as 0.1.6. For weighted entropy, weighted. We know the distribution as 40-60. So we'll write 40, 40%, that is 0.4, 0.811 plus 0.6 into 0.1, 0.924. Information gain of A will be 0.971 minus 0.924. We'll get it as 0.047. I'll solve it here only simultaneously so that it's easy to compare. For split B, C1 minus is outside, 5 by 7 log 5 by 7 plus 2 by 7. This is 20 by 70, so I'm cancelling zeros. Log 2 by 7. For child 2, minus 1 by 3 log 2 of 1 by 3 plus 2 by 3 log of 2 by 3. 0.918. For your weighted entropy, now here in child 1, you were having 40 samples. In child 2, here you were having 60 samples. Based on this, only your weighted entropy was calculated. Similarly, here for child 1, you have 70 samples. Child 2, you have 30 samples. So you'll have zero point 0.7 into 0.863 plus 0.3 into 0.918. This will be 0.879 and information gain of B will be 0.971 minus 0.879. So this will be 0.092. Therefore, favor B. Why? Split B. Because it is purer. It will reduce uncertainty more effectively. Child 1 is percent plus. So your answer is split B for your part D. First you had to calculate your information gain for your root, then for individual splits, and then you got your answer. That we are favoring basically split B. Next question is on a weighted KNN. You are given a KNN model of K is equal to 3 and the weight for a neighbor is 1 upon di. Wi is equal to 1 upon di, where di is the equilibrium distance. Then the query point, you're given 3 query points where d1 is 1, you get a negative class, d2 is 2, you get a positive class. And for 3 also, you're getting value 2 and a positive class. White is not visible on white. That's why when I'm writing on the question, it may not be visible. So I'll start writing from here. If simple majority voting was used, what would be the predicted class? Now, basically, in simple majority voting, each neighbor gets one equal vote, regardless of their distance. Now you have one vote for negative, two votes for positive. Therefore, who will win? Predicted class will be positive. Calculate the weighted vote for positive and negative, which class is predicted now. So we are given a weight formula 1 upon d of I. So weight for negative W1 is equal to 1 by 1 is equal to 1. For your positive, it will be W2 plus W3. 1 by 2 plus 1 by 2, you get it as 1. Since weights for both the classes is 1, there is a tie. Now, depending on the tie breaking rule, depending on tie breaking rule, the model might choose or it might pick the class of the nearest neighbor. That is your negative neighbor. So in B part, you can say there was a tie. Now, at what distance would the negative class lose its lead, assuming D2 and D3 remain at distance 2? Now, if we want to find out at what distance is the negative class losing its leads, this will happen when weight becomes less than the weight of your positive class. Weight of negative is less than weight of positive. We know that the total weight for positive is 1. 1, it's 1. So we'll write d of I and we'll put this as 1. So that means your di goes there. So 1 is less than d of I. So it will basically lose its lead. Negative class loses its lead when d of 1 is greater than 1. But when we say that d of I is equal to 1, there it will be a tie. But as soon as it increases from 1, the weight will drop below 1 and positive class will win. This was a easier question than the earlier questions because it is based on KNN model. So let's move on to the next question. Now this is a similar type of question. So basically, this is the same type of question where we are given the equal distances. So when we calculate weight using the formula given in the question, we get them as 100 each. Now we are given the voting. First votes for high risk. You get a score of 100. Then 2 and 3 are voting for your low risk. So saw plus saw, that is 200. Now we'll be voting for the highest total weight. That is for your low risk. Now, there's a B part to this question. This is a B part which says that now your new weighted votes are given to you. So here you are given a formula 1 upon di plus 0.1. So first we'll calculate the new weights. 1 upon 0 is the new one and plus 0.1. So you get this as 10. W2 plus 0.1, you get it as 1 upon 0.6. 1.667. Similarly, W3 is also 0.5, so you'll get it as 1.667. For high risk, we know W1 is equal to 10, right? And for low risk, It will be equal to W2 plus W3. 1.667 plus 1.667. This will come out to be 3.334. Now, the predicted class will change, will be the highest total weight class. That is high risk. So basically the answer is yes. The prediction has flipped. Has flipped from low risk to high risk. So this is your next question. This is question number 9. You're given an input of 32 into 32, onto which a convolution of 5 into 5 is applied with stride is equal to 1. This is based on your CNN concept. Convolutional neural net. So is applied with stride 1. If valid padding is used, P is equal to 0. What is the output size? So basically the output dimensions of convolution layer. The formula is O is equal to W minus K plus 2P upon S plus 1. W stands for your input size. K stands for your kernel or filter size. P stands for padding. S stands for stride. Now here in the question, you're given an input of 32, kernel of filter size of 5, plus 2 into padding is 0 upon 1, stride is equal to 1 plus 1. So 27 plus 1 is equal to 28. So output size is equal to 28 into 28. So first part, percentage of input area is lost at the borders. So basically a lost area is refers to reduction in your pixel. I'll write it down, pixel between input and output. Input is 32 into 32. Output is 28 into 28. So input area 1024, output area 784. So your area lost will be equal to 1024 minus 784. This will come out to be 240. Now we are told to calculate percentage. So 240 upon input size into 100. This will be 23.44%. Next part. What is the exact value of padding required to achieve same padding? Now you are given output size as 32 into 32. This is your output size. S is 1. You have to calculate what? P. So 32 output is equal to 32 minus 5 plus 2 into P plus S is 1 plus 1. So here on solving, you'll get the value of P as 2. Similarly, if you are given an input of 32 into 32, convolution 3 into 3. Next, let's use the next slide. So here you are given W as 32, K as 3 for convolution layer, stride is 2. Output layer is 16 into 16. We have to calculate is padding. 16 is equal to 32 minus 3 plus 2p upon 2 plus 1. On solving it, so this will be 15 is equal to 29 plus 2p upon 2. So this gives 30 is equal to 29 plus 2p. P is equal to 0.5. Now since padding must be integer, this is your padding. It is therefore not possible to get an exact 16 cross 16 output using symmetric padding. We are right now only talking about symmetric padding. But when we talk about your in practice, when we use in deep learning framework, when we use the concept of your asymmetric padding, this is also a concept. So you'll write, however, in practice, deep learning framework use this concept, asymmetric padding, where we use the value of p left and p right. And then we can achieve this size. This is optional if you want to write, but if you write not possible also, that's the right answer. Till here also it's fine. So this is the 10th question now. A CNN model and processes an image and results in a final convolutional feature map of size that is given. So this will be a flattened input size 7 into 7 into 512. This will be 25,088. You are given your dense, then a fully connected, that is dense layer with 4096 hidden units. So basically your dense layer units is also given 4096. So now your total weights. Okay, this is your A part only. So that's great. So your total weight will basically your input size into how many dense layer units you have. So the answer will be 102,760,448. So this is your answer. Next, new size of the final feature map if the input was 224 into 224 into 224. Now it is 448 into 448. Rest all stride and pooling operations are same. Therefore, spatial dimension in final feature map also doubles. Now original will be 7 into 7. Now new will be 7 into 2 into 7 into 2. That will be 14 into 14. So now your new feature map size will be 14 into 14 into 500. Calculate the new number of parameters in which the dense layer after doubling the resolution. So the new flattened size, we get it as 14 into 14 into 512, 1,352,000. Now your new total weight. Now dense layer units are same. So 1,352,000 into 4096. You get it as 411,041,792. Explain why this demonstrates that CNNs are translation invariant, but dense layers are not scale invariant. So first let's talk about translation invariant. Here we use the concept of basically a sliding filters or kernel, where like this is your matrix of an image. You slide the kernel of filter throughout the image. Now finding features anywhere is possible, and shifting an object will not break the model. Next, we'll talk about why they are not scale variant. So basically, why they are not scale invariant. One is that they require a fixed input size. Second, doubling image size will quadruple, that is 4 times the weight into 2 into 4. They cannot handle different image scales without changing the structure. So this is the answer. So this is question number 11, the second last question of today's lecture. So in this you are given 3 layers, each with the input, strides, padding, everything given to you in the question. Now a new formula that you know is parameters. Parameters is equal to width into height into input channel depth plus 1 for bias into the number of filters. If write this as number of filters. Now first of all, after layer 1, when you see the values, you are given an input size of 224. Then you put in the values and get the value. Depth will always be equal to the number of filters that you have. And you'll get your output. Similarly, after layer 2, you'll calculate the same thing. The pooling will not change. Now in C part, you have the input channel depth of layer 2, right? You have to check after layer 3, right? So layer 2 is the last depth that you'll go through. You'll have your last depth, your filter size. You put it into the parameter, you will get 4,640 parameters. Let's do the last part on the next slide. So now, your original layer, this is your D part. So your original layer, right now what we are doing is we are comparing the original single layer against the 2 new layers. Single first layer, that is your original layer, against the 2 new layers. Both setups start with one input channel and end with one input channel and end with 16 end output channels. So original layer is basically a 5 cross 5 filter, that is 5 cross 5 width and height into 1 plus 1 for bias into your 16 filters. This will be 26 into 16, 416 parameters. Now this was for your original. Now for your new setup, where you have two 3 cross 3 filter, you will add one 5 cross 5. For layer 1, it will be 3 cross 3 layer. So 3 cross 3 cross 1 plus 1 into 16. This will be 160. Now for the second one, you have 3 cross 3 into 16 inputs. Now after in layer 2 you had 16 inputs plus 1 into 16 filters. You get 2320. So here your total will become 160 plus 2320. This will be 2480 in total. Now your difference when you calculate 2480 minus first original is 460. You get 2064 parameters. Thus, you would add 2064 parameters. Now this I attached as a note. When we see a perfectly correct SVM setup, your positive support vectors satisfy the equation W transpose X plus B is equal to +1, and negative support vectors satisfy equal to -1. Now this is the last question on SVM. Here we have to find the SVM decision boundary. Now first step what we have is, first we need to find the hyperplane equation. This will be W1 x1 plus W2 x2. Here we have two classes, x1, x2 plus B bias is equal to 0. Now we assume the separating line as x1 plus x2 minus 4 is equal to 0. Your weights 1, 1, bias is -4. Now you check your classification at your different points. Take this as your function, decision function, decision function. Now take the points one by one. So let's say 2, 2. So f of 2, 2 will be equal to 2 plus 2 minus 4 equal to 0. Now this point is lying exactly on boundary. On boundary. Thus, it will be one of the closest points. Therefore, it is a support vector. Similarly, f of 4, 4 will be 4 plus 4 minus 4, 4. This will be positive, therefore it is of class +1. Then 4, 0 will be 4 plus 0 minus 4 is equal to 0. Same thing, this is also support vector. But this will be of class of -1. Next, for 0, 0, why are we saying class -1, class +1? Because it is given in the table if you may see, right? So now for 0, 0, it's 0 plus 0 minus 4. This will be -4. This is negative of class -1. Now, another thing that you have to find is the margin. Now, the formula for margin will be 2 upon modulus of W. This will be equal to 2 upon under root of 1 square plus 1 square. So this will be 2 upon under root 2. This answer will be under root 2. So your hyperplane is this. Your weight vector is 1, 1. Your bias is -4. Your margin is under root 2. And your support vectors 2, comma 2 and 4, comma 0. So this is the answer. So thank you all. This was all for today's lecture. If you like the video, do like, share, comment, and subscribe to my YouTube channel. If you have any doubts, do mention them in the comment section and I'll try answering them as soon as possible. So thank you. Bye bye.